I'll be brief. And my great pleasure to introduce Mark Ayres to talk today. Mark's actually a PhD graduate from my group, started first with Kelvin and then finished up with me. He came to Colorado to work in the magnetic storage industry, which therefore make you curious why the heck he's talking to us today. Hopefully they'll make that clear. The reason so he came and he's now in holographic data storage, which maybe is the first hint. He mentioned to me that he has very strong holographic credentials because he's taken a few classes from a guy named Leith. The reason I nominated him to talk to this group is I think his research that he's going to talk about is a really fantastic combination of optics and signal processing jointly optimized, and I think that therefore hits a COSI topic. So I understand also he has a cold, so we all have to listen very carefully.
Yeah, sorry about that. I'm going to hopefully not wear out my voice by the end of this, but please listen carefully, I guess. Is there a clicker, or do I just walk over here to do that?
No, just
okay. Oops. Get this all. So I'm going to talk about the holographic data channel for InPhase's holographic data storage product, and I'm also going to talk about my ideas for the second generation, which will be the second half of the talk. A lot of this material was in my dissertation, so some of you have seen some of it before. I have some new stuff in here as well, though, so hopefully it'll be interesting enough for people who have seen that. Outline of the talk, I have just a few slides on holographic data storage just so I can sort of get people understanding what it is we do, how we record our data, and then I'm going to go into the existing data channel and the future data channel, the two halves of the material here. The existing data channel is a direct detection with a photodetector array, and the primary topics that we need to address are how do you measure the alignment of the holographic image and resample it back into the original SLM image that you stored. The future data channel, I'm proposing using a coherent detection, so we're going to get phase information out of the channel and hopefully get some improved performance. So here's InPhase's first slide for every slide presentation to the outsiders. This is just a very coarse overview of what we do. We're going to split a laser beam in half, use one half to illuminate a spatial light modulator. We're going to take the data we want to record, digitize it, and then compose it into a 2D array of light and dark pixels. And then we're going to take and form an interference pattern with a reference beam within our volumetric medium and record a hologram. This is attractive from the standpoint of a recording capacity because each individual hologram essentially gets a storage density as though it was dictated by the 2D resolution, like a DVD or a Blu-ray disc. And then on top of that, because of volumetric effects, we can multiplex many holograms, hundreds of holograms, into the same volume of material, so we get a multiplying factor and we achieve high volumes of storage. And we also get, in theory, pretty high transfer rates because we're recording and recovering a whole page of data, which is more than 1 million bits of data at a time, and are able to use parallelism in order to keep our transfer rates high. The way we're doing this is we have to stop and start the medium so that we have stability to record, the fringes interferometrically. And down inside the medium, it's a photopolymer system where we have one photopolymer is pre-developed, or one polymer is pre-developed. We call that the matrix, and it basically provides a support where a second system of monomers are dissolved in the solid, and they can diffuse around inside there. So when we expose the medium with the holographic signal, we get a fringe pattern, and that causes local polymerization of these monomers. And once the monomers have densified from the polymerization, we get diffusion of the remaining monomers back into dark areas, and it's mostly this mass transfer of the diffusion that drives a change in the refractive index, which makes the index gratings that we record our data in. And then when we're all done, we flood cure it, and we use up all the leftover monomer and other photoactive components, so we have what should be a nice, solid data structure made of covalent bonds, which it has a long archival life, unlike, say, magnetic recording where you have metastable magnetic domains, or your flash memories where you have little bits of static electricity on floating gates. So that's one of the big points for the advantages of this technology for archiving data for long run. And there's a metric for how much recording you can do in a medium. It's called M number, and it goes as the number of holograms times the square root of the diffraction efficiency of those holograms. And that's a very simplified metric that I have some problems with, but everyone uses it, so I'll just leave that up there as M number as our medium metric. This is an outline of InPhase's architecture. We call it a phase conjugate architecture. What happens during recording is we illuminate the SLM, we create a Fourier transform of that data pattern and aperture it so that we've shrunk down to only the minimal Fourier components that we need to reconstruct the data. Then we use a 4F system where this last lens is a fast storage lens, so we can make the smallest possible spot and make another Fourier plane in the middle of the media, interfere it with a reference beam, and record our hologram. When we come to recovery, we actually illuminate our hologram from the opposite side with a counter-propagating reference beam, probe beam actually, and that produces a sort of a quasi-phase conjugate reconstruction actually, but it causes a counter-propagating phase conjugate reconstruction to propagate backwards. During reconstruction, the aperture, which was during write, it was used to clip the signal to the minimum amount, and during reconstruction, it actually filters out adjacent holograms so that it's doing what we call polytopic multiplexing to increase our density, and then we get an image on the camera and extract the data from that. And just so you can sort of see what this looks like, it's a 5 1/4 inch form factor removable media. It's got a light tight cartridge on it, and our first generation stores 300 gigabytes at a 20 megabyte bit or byte per second read and write transfer rate. This thing is meant for data centers and non-consumer applications, so you're not going to see this in the stores anytime soon. Right now, this is only being shared with our super secret group of evaluation customers, so you can't even buy this yet, but we're hoping it'll be out sometime soon. Okay, so let me go on to the data channel. The Tapestry is the name of the device I just showed you the picture of, and we have the 2 steps. For this 2-dimensional data retrieval task, we're going to, again, as I said, digitize the data, and we're going to get an image with nice, sharp on and off pixels. When we record it and recover it, the hologram, owing to the fact that we've clipped down the resolution to the barest minimum we can get away with, we're going to have a lot of blur. And then we're going to have distortion of the image, and I've represented that as this Q function because of thermal effects that are going to sort of distort the image. We may get a magnification or a rotation due to just the alignment of the media or the temperature. And we also get higher order distortions, which have to be accounted for. And then to make matters worse, we get noise, which is the worst part of the noise is the coherent noise, which comes from the same laser. So it goes inside the modulus squared, and that causes a lot of problems for us too. And the processing of each page is actually more involved than I'm going to talk about it, because the first thing we do is we decode some barcodes around the edge and get a coarse alignment of where the image is landing on the detector. Then we do this part that I'm going to talk about, which basically is the task of restoring the state of each SLM pixel by measuring the alignment and then resampling the image we get. And then after that, we have to calculate log likelihoods. In order to feed it into a soft error correction, we have to do interleave, and we have 3 different layers of error correction, which adds up to a lot of overhead to get back to the user's data. But I'm only going to be talking about essentially the image processing step of the channel. So if you were to zoom into just a very small piece of the SLM and imagine what that image of that looks like as it impinges on the detector, you get a fairly blobby-looking, low-resolution image. And if you were going to detect the state of each pixel, the first thing you would think of would be to line up a detector pixel, which is these square boxes, so that each image of an SLM pixel lands right in the middle of a detector pixel. And, excuse me. This is the way that a lot of experiments were done on holographic data storage basically over decades, because this project has been, or this technology has been pursued for 40 years now. But it turns out that this is an impractical way to make a real system that you would want to ship in the field, because a misalignment of a few microns will cause your pixel images to miss the detector images, and the SNR drops very sharply. And if you have any of these magnification or distortion problems I'm talking with, you cannot pixel match all the way across the image, so you really have to come up with a better solution. So the first thing you would think of to do that would be, of course, to oversample the image. And what I'm showing here is an oversampling of 2 in both directions. So it takes 4 detector pixels for each transmitted SLM pixel. And in this case, you can work out a pretty simple data channel that will get you high SNR regardless of what the alignment is. And this would be the minimum Nyquist requirement to sample this irradiance pattern as it impinges on that detector when the aperture is at the very minimum it can be in order to transmit the data. And even with that minimum, we have 4 times as many detector pixels we have to process in order to get to our data pixels. But this is the way 4 pixels or even 9 pixels that several of the companies that attempted to do this before us were proposing to do it. And there's something of I guess you would call it a false conclusion that you can reach that you need to do this 4x4 because you need to sample the irradiance, but you really don't. You can oversample by a smaller amount than this and recover the data, and I'll be talking about that later. But this guy Jeff Burr was writing papers about doing very slightly oversampled image reconstruction before I started, and he actually did some consulting with us at InPhase, but we never quite got that system working right. But anyway, let's leave aside the oversampling, and I'm just going to plow ahead and show how you might do all these steps of detecting this alignment and then doing the resampling to get to the pixels. So the first step is to measure the alignment of the whole image, and we do that by embedding these known fiducial patterns within the image, and we do that on a grid which is 64 SLM pixels on both ways, and each one of these is 8 by 8 pixels, so that makes only about 1.6% overhead, so it's not too much. I've removed all the data here. And what we're going to do is when we get the detector image, we're going to do a pattern matching operation to find these known patterns as they land on the detector array. And we can display that information in the form of a offset from the nominal, where every one of these reserve blocks would land at a nominal position if there was no distortion or no movement. And if we display this offset, we get this thing we came to call a quiver pattern, because that's the MATLAB function that plots these arrays, which gives you a visual representation of what's going on in the local distortion of the image. And we exaggerate the size of the arrows. This is probably a fraction of a degree of rotation blown up 64 times, so we can see what's going on. Okay. So when we do this pattern match, which is basically a cross-correlation operation, we're going to look for the known reserve block pattern and find the peak of a cross-correlation within a small window. There are two problems with that. One is that you will get false matches due to the data pattern, which you have no control over, which can look like the data or look like the pattern you're looking for. And furthermore, if you just look at the autocorrelation of the pattern that you're looking for, if it does not have a sharp peak, then it will match even when it's not giving you an indication of where the reserve block really is. So the condition you want to enforce to make that to minimize those two problems, the first condition is you only want to look for a target that corresponds to the center of this pattern, because you want it to be surrounded by known data and not by random data. And then the second condition is you want to have a very sharp autocorrelation peak surrounded by nulls on all sides. And the way I came to generate these patterns was just by a computer search. I started with certain constraints on these patterns. You can see it has a symmetry about the origin, inverted symmetry about the origin, and that we use these to calculate our SNR on our pages and other things too. So I was able to just add this constraint of finding patterns where the cross-correlation between the inner 6 by 6 and the entire 8 by 8 has this null around the central peak, and that greatly reduces the amount of noise and also makes it so that the data surrounding this does not enter into the measurement that we're doing. So when we perform this operation on the whole page, it goes something like this. We take the known pattern, take the center 6 by 6, and resample it up to whatever the oversampling ratio we happen to be operating in is. And I haven't defined that yet, but this happens to be a 4/3 oversampling ratio. And we get an image of what that pattern is going to look like when it's on the camera at a specific alignment, but that doesn't hurt us too much. Then we go into the image and we pick the smallest possible window where each one of these reserve blocks could land given the coarse alignment we detected with the barcode. And then we do the cross-correlation operation. And for this, I actually, a long time ago, picked a real image. This is a real fragment of a camera image, and you really have to squint to decide where this pattern lands in that. It's not at all apparent by eye where this is anywhere, but the cross-correlation picks it out pretty cleanly. And when you then go and find the maximum value in this cross-correlation array and interpolate among the values constituting the peak, because the peak is actually bigger than a single location in this, you can find the actual alignment of this reserve block on this page to within actually just a few % of a detector pixel in an RMS average. It really works surprisingly well. And once you have the fiducial locations of each of these reserve blocks, you can now interpolate in between all of them, because this should be a slowly varying function, and you know where every single SLM pixel image lands on the detector array, which is important for the resampling. And another thing to point out, which is going to be in the second half, is that the strength of this peak, which I could get by summing the values that are constituting it, gives us sort of an unscaled covariance, which is going to be useful for determining determining the phase in the second half of the presentation. Okay, so after we know where every SLM pixel lands on the detector array, we need to resample the detected values and turn them into estimates of what the SLM pixel states were. So, and I do that by probably a straightforward method. Probably the first thing you try is as a linear filter, where I take to any given SLM pixel image, I pick the closest 4x4 neighborhood of detector pixels. That gives me 16 values to go into, and then I use 16 coefficients and just use that to determine an estimate of the state of this original SLM pixel. The catch here is because the SLM pixel may land anywhere inside this box. The center of it may. So we have a lot of different subcases of local alignment that we need to account for in order to make this work well. And what we actually do is we separate this box into 16 by 16, so we have 256 separate cases of local alignment, which gives us 256 flavors of coefficients that we could use on any individual pixel in order to do the resampling of that pixel. And another trick I'll talk about in the following slides is, before we apply the coefficients, we take the square root of the detected values, so we get unsigned magnitude rather than magnitude squared of the detected values, and it turns out that just makes the transformation more linear, and it gives a better resampled values. Okay, so in order to determine those coefficients, here's the business about taking the square root to get to the magnitude. So what we can do is arrange our 16 coefficients times our 16 values within the window, and then for each row we want to span all of the cases of the data that may appear, of the pattern that may appear inside that window. And the pattern is inside that window is primarily determined by the local state of all the SLM pixels that are in that window. And since there's the pixel you're trying to detect, and it has 8 nearest neighbors, there are really 512 local neighborhoods that are primary that you need to span over. But actually, you'd even rather do more, because you'd rather look 2 pixels away from your neighboring one, but that becomes impossible to do systematically. So what I do is I usually did several groups of the 512 in order to make this matrix problem, where I know the actual data state, which is a 0 or a 1, and I compose this matrix, solve it. This is just least squares of this matrix, and then I get my 16 weights, and I do that for every single one of these 256 cases. So there's a whole lot of computation going here to crank through the set of coefficients. And I can also do it either by simulated magnitude values or with real magnitude values. I've done it both ways, and it comes out eventually a little better when you use the real ones, which is not too surprising. Another thing to point out is, because this is solving for zeros and ones, it's not really a resampling as in a rate conversion like you do on your MP3 if you're trying to resample your music. It's trying to establish the actual value of that pixel as a binary value rather than the intensity that lands at the center of that pixel, because the intensity that lands at the center of that pixel has a lot of nearest neighbor noise, or ISI, that we actually want to remove. So this is a filter which also does a sort of a first order deblurring of the SLM pixel. And then when we're done with his weights, we can go back and apply the weights to the values we used and come up with our d hat, which is our actual predicted values. So these will now be, sort of grayscale attempts to get zeros and ones, and we can look at how close, on average, the ones that were supposed to be ones minus the ones that were supposed to be zeros are over the variance of, or the standard deviation of the ones that were supposed to be ones plus the ones that are supposed to be zeros. And that's a metric for how well the SNR is being recovered from the image. And this is just a plot showing how that linearization step I talked about works. This was written about a long time ago by Kumar, a student here. I actually spanned a lot of different values here, and I found that the peak is a little bit higher than 0.5, which I think has to do with the fill factors of the SLM of the detector pixels. But basically, you can see that if you take a square root or near a square root, you get a pretty significant boost in the SNR, which says that the problem, the matrix that you're solving is just more linear and has less of a residual in that regime. So we do it. But this is kind of an illustration of the problems of doing this with coherent light, which I'm going to address in the second section. Okay, so now coming back to the problem of deciding how much oversampling you do. What is the detector pixel pitch you're going to really use with this whole method? The whole method I just outlined you could do with any ratio of oversampling. So what I did is I just sort of exhaustively scanned from 1 to 1, which would work in a pixel max match case, all the way up to the 2 by 2, which is a Nyquist case. This is the linear oversampling ratio. And I picked 3 of those 256 different local alignment cases that should sort of bound the performance. So the first case here is when a SLM pixel image lands smack dab on top of a detector pixel. That you should expect to be the best case, because you'll get a nice clean signal from one detector pixel. And then this should be pretty much your worst case, where the image of the pixel you're trying to recover lands right between the corners of 4 detector pixels. And there's nothing you can do about that. You just have to do the best resampling you can in that case. And not surprisingly, that's really poor when the detector pixels are the same size. And then I have an intermediate case where it's off by a quarter in both cases. So all the 256 cases should sort of form a caustic of lines within that envelope. So when you rework that whole problem, re-extract new coefficients and redo the simulations over and over for these 3 cases, you can see that you get a very quick improvement of this worst case resampling SNR, which is limiting the performance of the whole system. Doesn't matter too much, not surprisingly, when in the well-aligned case what you use, and it's sort of in between in the in-between case. But what the curve shows you is a nice knee coming in here about the 1.3, 1.4 range, where above that, more oversampling really only gives you diminishing returns in the performance you're achieving. So operating out here like people were assuming you had to is not buying you much bang for the buck. So based on this, we started doing experiments at the 4/3, because that provides a nice ratio of available pixel sizes in detectors and SLMs, and went with that. And that gives us the ability to recover our images with only 1.77 times as many detector pixels as SLM pixels. And this was the very first experimental data that was validating the whole procedure. We had, again, in the past we were doing the pixel match where you had to very exhaustively align your image so that your SLM pixels were landing right on top of your detector pixels. So we constructed a system where we could actually swap out the camera and take the same hologram and recover it both ways. And you can see that the pixel match version, which is blue, well, the oversample detection method actually improved the quality in all cases, and maybe even more significantly in this marginal case where I think we knew what was wrong with this, but this was a few years ago. This was a marginal stack of holograms. The resampling case actually degrades less than the pixel match case. So we think we're onto something that's a little more robust as well as being well, practical. Okay, so here's a sort of this is a modern page image showing the positions of the reserve blocks we actually have in the product. A lot of these other ones I showed you were smaller pages, but this color codes the SNR. Anything that's yellow or higher is good, and then the arrows show that this image has a whole bunch of rotation, which is pretty common. Magnification is pretty common. Shifting the image around, that can be up to tens or 100 microns or so. So that has to be code for. If you look at the original image, you can see it looks kind of blurry, and the histogram has sort of this decaying wide shape. When you resample it, it gets sharp. And now we can tell which ones were the zeros and the ones, and we can color code them. But you can see you have a nice peak separation between the zeros and the ones. So you can now begin to believe that you'd ever get the data back out of that. And this is my movie from probably 5 years ago when this first started working. But this shows the decoded image being done in software. This is all done in FPGAs now, where off-screen someone is twiddling micrometers to just crank that camera around so that the image lands in different places, and you can see the arrows are just shifting wildly, but the separation between these two peaks and the SNR doesn't really change. This is the SNR plot. Doesn't really change much as that's going on until the very end, where the image actually walks off the edge, and you can see a blue bar where the SNR crashed. So this was a demonstration that this is a pretty robust method, and it is being used in InPhase's product. And I think that's the last slide for this, and I'm ready to talk. Okay, I guess we're doing okay. About what I would hope to do to this channel for future generations, and I'm going to talk about, actually let me go to the next slide. I'm going to talk about this in the context of how we would get to some things you might want to do for a product, and just speaking as an engineer, this isn't a marketing plan for InPhase or anything. It's probably not very interesting to the company unless we at least double all the important specifications. So we sort of want to double the capacity and double the transfer rate. And furthermore, from where we are to where we would like to be, a terabyte's a nice round number. So I want to try to make the case of getting to a terabyte on one of our cartridges with the things I'm going to talk about. The three factors that go into the capacity, or the density, depending on how you look at it, are the address space. That's basically the number of different independent gratings you have to work with inside the medium. The signal strength, which comes from the diffraction efficiency, which comes from the medium dynamic range, but also the efficiency of usage of that dynamic range, because the way the system is composed, you can get more diffraction efficiency in some cases using less M number. And then the noise is obviously the limiting factor. This intrinsic scatter is just the noise that the media is going to cause, whether there's a hologram there or not. And that's usually our noise floor, and we try to make sure everything else is below that. Recording-induced noise, I have a couple slides on here I'll show you about, but if you do your holography in certain ways, it becomes very noisy on its own. And then the detection-induced noise has to do with what is the ceiling of your SNR, and I'm going to try to show that this coherent detection works a lot better than the direct detection. And then, of course, for the speed, you're going to need to increase both the recording and the recovery rate. So I have a few comments about those. Okay, so taking those three numbers, the address space and the signal power and the noise power, I'm going to call this Shannon abuse, because this equation is actually the Shannon capacity, which is going to tell us the absolute maximum channel capacity or disk capacity that you could get. But I'm really going to use it by plugging in numbers near where we're operating, which are not very close to the Shannon limit. That's pretty hard to do. And just look relatively what's happening with the terms in this equation. But anyway, you can think of the bandwidth is like the address space. And then this whole term is sort of like the code rate you get from your raw bandwidth to turn it into real data. And your signal power goes sort of as your hologram diffraction efficiency, and your noise power goes as the noise, essentially, diffraction efficiency. And where we are right now is we're getting 300 gigabyte capacity using a really low code rate because we have all these layers of error correction. And we have to do that because we have this low SNR that we're dealing with. And that means that we're really using 700 gigabytes worth of raw gradings to produce 300 gigabytes worth of user data. So going into where does address space come from, you can think of this as the accessible degrees of freedom that the physics of the recording technology provides you. So if you had a Blu-ray disc and you're focusing your light down to a spot, it's pretty easy to imagine on a two-dimensional surface that your capacity goes as the resolution of your spots. In our holographic recording, our degrees of freedom go as the number of gratings you can put into a volume. And you can count up that maximum of that by looking at the X, Y, and Z components and doing this is sort of the same thing as the Planck black body argument, where if any side changes by an integral number, you have a new orthogonal mode that tells you that grating is different than the other gratings. And fortunately, we have a nice set of physics with the Bragg effect that lets us access these gratings with very little crosstalk with each other. You can imagine there's very little crosstalk in spots that don't overlap. Well, there's also very little crosstalk with gratings that are orthogonal to each other if you've recorded nice, clean gratings. But there's a bunch of other stuff that wants to get recorded while you're doing holography, which is not so clean, and it causes a lot of noise. So if you look at the interference equation for the spatially varying intensity pattern inside the media, you've got terms for the reference beam and the signal beam alone, and then you have all the cross terms between the reference beam and the signal beam, which are the data gratings you want, which are those nice, clean Fourier modes. But if you look at this signal term and blow it up, it has all kinds of other garbage in it that you don't want. So I'm using P for pixels. You can think of modes if you were in a different one, but each pixel within the signal beam has its own independent DC, and then you get a cross term for the interference with every pixel with every other pixel being recorded into the media. And because there's something like 1 million pixels, there's something like 10 to the 12 of these terms. Excuse me. And they are manifested as structure in the intensity pattern in the signal beam inside the media. So this would be a Fourier transform of an SLM modulated with our data, which sort of looks like a cross-section of the intensity inside the media. Now we actually clip it down to this, approximately the size of this rectangle, because that's the size of that aperture which passes the minimal amount of frequency information we need. And it has inside it this huge DC spot where all the DC components focus, and the intensity is something like 100,000 times brighter than the neighboring signal. So that's a huge problem right there, and that's sort of a nonlinear regime that causes the media to saturate and actually distort, and bad things happen. If you look at another regime and analyze what happens to all these independent cross gratings, even in the linear regime where there's no worry about the saturation effects, it turns out all these gratings want to be coherent with each other, and they're going to cause a lot of noise, and they are Bragg matched to the object beam or the signal beam itself, because they were written by it, and so they're going to cause every pixel to want to diffract into every pixel and just generate this nasty haze. And given a couple references, well, let's not worry about that. Now, I hope I can explain this slide sufficiently, because it really probably should be several slides to go over this development here. But I just wanted to give sort of a description of how you get rid of, or how you lower the impact of that intrasignal term, or that causes all the problems. So this would be sort of a cross section. Here's the photoactive layer of the media, and then there's some substrates on either side. The signal beam comes in, it focuses down to a Fourier plane, and then the reference beam comes in and envelops it, and then you get fringes in the overlapping area. You take the 3D Fourier transform to get into K-space of what's going on here. And in this regime, the complex amplitude of the signal beam lands on the K-sphere along this arc, and it comes out of the plane. The complex amplitude of the reference beam lands on this arc, and it doesn't come out of the plane. It's for our angle multiplexing. And then the gratings with the data that we want can be represented as a cross correlation physically in the 3 dimensions of this patch on a sphere with this line on a sphere to produce this envelope out in the grating space. And then you also do the other cross correlation to get the conjugate band of the data. So the troublesome term I was telling you about is the autocorrelation of this signal patch. So this is the autocorrelation of this patch with itself, which produces this sort of butterfly-shaped envelope inside. And you can imagine that if this was just a DC value, that this would have a very high value, would sort of get the triangle shape of two DC terms cross correlation with each other, and you'd get this shape plotted here in false color. You'd get a very high pedestal around it, representing all these noise gratings that are going to cause a lot of problems. Now, if you can imagine then instead that you are going to start doing something like twiddling the phase so that the phase varies slowly and the DC phase is 0. And now you're imagining doing an autocorrelation between two DC balanced functions. You're going to drive it to being more of a sharp spike with just a little bit of residual noise on the bottom. So that I'm trying to give a sort of a graphical intuition of where this noise looks like, even though you can come at it from a bunch of different ways. So you have to do something to drive this pedestal down and well, basically make the data recoverable. What we do at InPhase now is we put a slowly varying phase mask in front of the SLM. That causes the phase term along this arc to twiddle around and make it close to DC free, and that drives it down to something that might look like this. What I want to do is I want to make the phase variations in this arc as fast as possible to drive this down as far as possible. And the fastest way you could do that would be to modulate each pixel with its own phase, and instead of modulating them on and off, modulate them 0 degrees and 180 degrees. So we're doing what's called phase shift keying instead of amplitude shift keying, where we're turning the pixels on and off. So that's the first proposal for this second generation, is to do phase shift keying. And because you have the fastest possible modulation, you get the best suppression. So my claim, which has yet to be proven because this is well, I haven't done the experiments yet, and this is second generation stuff, is that if we go to phase shift keying, we can get rid of the phase mask. And that's going to be an important thing that needs to be proven, but if it does work out, it's going to be great news, because the phase mask is nothing but trouble, frankly. It's just more parts that have to be very carefully aligned. So the first task is to do phase modulation. I have a slide of what it looks like. Instead of having pixels on and off where we have dark pixels, we're going to have them on and on with 180 degrees out of phase from each other. If you go through arguments that you can find in a lot of communications books, which I'm not going to try to talk about here, going from ASK to PSK modulation, other things being equal, will give you about 3 dB of improvement in your sensitivity. We get rid of the phase mask. We should effectively close to double the M number efficiency to get the same diffraction efficiency, because in our system, I didn't mention this, but the reference beam generally has several times most of the energy, and the signal beam has less. So if we turn on half of the pixels, we're going to get twice as many gratings diffracting and almost twice as much diffraction efficiency. So we get more M number efficiency, and then furthermore, we have the opportunity to get more light through the SLM because we're losing less on those dark pixels. And of course, this brings up a problem, is that we can't detect opposite phases directly. So, of course, the answer to that is to use coherent detection, where we're going to interfere a local oscillator, mix it with our signal. So if you look at direct detection, where we don't have the coherent detection, you can see that this red line would be this the complex amplitude going plus and minus, indicating zeros and ones, and then when you square it to detect it, you can no longer distinguish between the zeros and ones. You've lost the information. If you mix the local oscillator, in this case I'm just showing a local oscillator at a value of 2, so it's a very small one. You're basically taking this signal, shifting it up by 2 before you square, and now you can distinguish the zeros and ones from each other. And not only can you do that, but you have a whole lot of amplification. You have a much bigger signal to detect, so that's going to come in very handy. The catch is that you have to match the phase of the local oscillator with the signal very precisely, because if you're off by fractions of a wavelength, you will either invert your signal, which is this case, or if you're coming in at plus or minus 90 degrees, you'll lose your signal altogether. And So what I going to do here is go ahead and describe how to mix this local oscillator in, and then I'll come up with a solution for the phase problem as we go. And going to coherent detection should also provide higher SNR than direct detection, just based on analysis you can find in communications books. Okay, so the other thing that happens is when you use the coherent detection, here's the direct detection case. When we have coherent noise added to our signal, we get a cross term including both the signal and the noise, which effectively makes the noise interact non-linearly and causes a great variance in the detected values, so causes a lot of SNR loss. When we do the homodyne detection, we're now adding this strong local oscillator and doing a three-way coherent sum, so we get three interference terms between the two of them, and because we're going to use a local oscillator which is stronger than either of these terms, the terms without the local oscillator shrink by comparison. So generally, the cross term that caused all the trouble is going to fade in significance, and we're going to have amplified signal and amplified noise, but no cross term between the noise. And furthermore, we're going to see the phase of the signal. And I went through an argument that said that that's worth about 3 dB of improvement in your signal to noise ratio. Okay, so if we're going to do that process in the architecture I showed at the beginning with that phase conjugate architecture, simplest thing you could imagine doing is just during your reconstruction, you're going to use a non-polarizing beam splitter, put a big flat plane wave into the signal path so it mixes with the with the diffracted beam and is detected at the camera, giving you all these benefits supposedly. Problem is that this has no control over the phase that's going to result on the image. In fact, it's going to change throughout the image because there's going to be some slowly varying phase carrier depending on the environmental conditions when you reconstruct your hologram. So what I'm putting in here is a switchable retarder. I'm calling it a ferroelectric liquid crystal quarter wave plate because that's probably a likely candidate that would do this. This is a switchable retarder that can vary the path length through this arm by 0 or 90 degrees. So we have the ability to control the phase that it mixes at. Oh, and the other point is that you probably want to make this non-polarizing beam splitter pretty lossy so that most of your signal goes through here, and you sacrifice the local oscillator beam in preference because the diffracted photons are the precious ones. Boy, better get going. Okay, so now if you imagine that that device operating, you can take two separate images of the same hologram. You'll get slowly varying regions where the local oscillator is in phase, so you have high contrast. The local oscillator is 180 degrees out of phase. You have inverted contrast, you can tell by the border. And then you'll have regions which are near 90 degrees, so you'll have low contrast. And then the second image will be a complement to the first one, and you'll see that all the regions that were low contrast will be high contrast in the other one. And you can imagine having these two images that you can now come up with a method of stitching together the images and getting the high contrast in all pixels. Okay, so in order to determine what's happening in that phase, we're going to go back to those reserve blocks that I used for the resampling step. So now, if we end up with an inverted region of the image, we're going to see an inverted copy of the target pattern we're looking for, and that's going to produce a negative going peak in that cross correlation operation that we do in order to do the alignment. And so what we're going to do is we're going to take and modify that quiver operation where we're going to find the strongest peak regardless of its polarity and record both its position for the resampling that I talked about and also its height. So we're going to get this map across the image of the cross-correlation peak strength in both the P and the Q images of those image pairs. And that looks something like this for those two images I showed you. The bright shows where it was in high contrast. The black shows where it was inverted in high contrast, and then the gray shows where it's out 90 degrees out of phase in low contrast. And now we can estimate the difference between this local oscillator and essentially the wavefront carrier of the hologram by taking a four quadrant arc tangent of the peak strengths. So we now have a measurement of what the actual phase is doing across here. And furthermore, it should be slowly varying because we've introduced because the hologram should be on a slowly varying carrier coming out of the whole medium. Okay, so and then we're going to take this and we're going to upsample it to every position on the image, and we're going to combine the two images that we took, those quadrature related images, using this formula, which is basically the sine, or the cosine and the sine of the local oscillator difference. This is going to restore the negative regions to positive polarity, and it's going to combine the it's going to combine the two images in proportion to the available signal, and give us an image that appears as though we had phase matched that local oscillator to the whole image over its entire field. And then we can go and resample it and get our data back to the original method I showed you before. Here's some simulation. I'm going to skip this one because I have this as sort of duplicated in another slide, and we're really going late. One of the things we're going to have to be able to do is these green boxes show approximate locations of the reserve blocks on this image, and these fringes, this is one of the few experimental things I have for this yet, show a plane wave interfering with one of InPhase's holograms, and we can see the fringes where we have the positive interference, and then instead of the negative interference we have dark regions because it's ASK modulated. But anyway, the point of this slide is that we're going to be very sensitive to the number of fringes, as we're going to have to be able to estimate this fringe carrier based on these samples. So first thing is we might need to Nyquist sample the fringes as they appear on this. We might be able to do a little better than that with parametric fitting. And also we're going to be sensitive to media mispositioning, because positioning of the media, the media is in the Fourier plane, so positioning in the media turns into fringes in the image plane. I guess I'm not going to elaborate on that too much. Okay, so now I promised address space as well. I have a whole method here that's going to give improved SNR and speed. This is how we get more address space. Complex wavefront, which we're now detecting with our coherent method, has two channels, and we can put another hologram on the other channel. And this is analogous to doing quadrature amplitude modulation, and it works because the two carriers of the same frequency are orthogonal to each other, just like neighboring frequencies are orthogonal to each other. So my argument here is that this really is doubling the address space accessible to the holographic device and doubling the capacity. So what we need to do is we need to record a second hologram, which on these images will appear in the voids where there's low contrast here. And I call this phase quadrature holographic multiplexing. So in order to record in phase quadrature like I just said, we're going to now take that switchable retarder. It's probably the same one we use for the recovery. And we're going to use it during the recording phase to change one of the arms, and it could be either of the arms, by plus and 90 degrees. We're going to record 2 holograms with the same reference angle, and we're going to end up with 2 holograms where one hologram, the fringes occupy the 0 and the 180 phase state, and the second hologram, right in the same angular band, occupies the 90 and the 270 degree phase state of fringes in the media, and also in the complex wavefront that's going to be reconstructed when you recover that hologram. And you could really do a better job if you could do that all on the SLM if you had a 4-level SLM, but I guess I won't talk about that. Those tend to be slower devices. Okay, now in order to recover the 2 holograms that are now going to be simultaneously reconstructed by the same reference beam in phase quadrature, we'll just recover the first one using the method I already outlined. It's going to reject the out of quadrature signal from the other hologram. And then we could go and just reapply that algorithm, that whole algorithm independently to recover it, but we might as well use the information we've already got. So we'll take the same pair of images and the same cross-correlation maps, and we're going to do basically the minus sign cosine version of the matrix rotation to get the quadrature image out of the same 2 image maps. And what this does is that it gets us back to we take 2 images, and we get 2 pages of data out of those 2 images, even though they're entangled with each other. And furthermore, we're back to only doing one set of cross correlations, which is sort of computationally expensive per image detected. And the thing you're going to worry about when you see this is how bad is the crosstalk between these 2 images, because they sort of occupy bands that are close to each other. So I did some simulations, and I haven't really spanned all. Okay. The first thing you want to do is you want to apply the same equalization trick to prevent the reserve block pattern in the 2 images, which are going to be reconstructed, superimposed on top of each other because these are blended images. So I want to make the cross correlation between one image's reserve block and the center of the other ones have a 3x3 null in the middle, and vice versa to have a 3x3 null, so that there should be minimize the crosstalk between both the positions and the peak strengths in that cross correlation. Okay, so here's the simulation results, including both the homodyne case and the multiplex homodyne case. Here's our baseline. This is what we have now, where the optical power to the optical noise is the input, and then the function here is the detected page SNR according to that formula I showed earlier. So when we go from the direct detection to homodyne detection, still using the ASK, we get a couple dB. And then when we go from the ASK case to the PSK case, where we have the quadrature homodyne without that second hologram causing noise, we get this green one. So this is sort of the baseline case. So the question is, when we add the second hologram in quadrature with the first one, how much does that degrade compared to the case where there's not another hologram to cause crosstalk? And I was able to optimize the algorithm enough to get that under 1 dB here. You know, this direction here, these curves, the red curve, which is the the quadrature multiplex case is hugging the case without the quadrature hologram pretty tightly, which says that the crosstalk between the P and the Q holograms, the quadrature multiplex hologram, is probably manageable. Okay, yeah, I think this is pretty close to the end. I have my summary showing what happens to those terms on the Shannon one. So doubling the address space gives us our number of raw gratings going from about 700 gigabytes to 1.4 gigabytes. If we get the plus 5 dB, which is what I showed in the simulation, but it's not necessarily what I expect finally, then we're getting this term almost doubling. So with those together, we're in the range of getting a terabyte on the InPhase form factor disk without increasing numerical aperture resolution or all the hard things, angles and multiplexing address space. So just with doing these tricks I'm showing here. And on the transfer rate, we don't have to change the reference beam angle. We only do that half as often. The recording exposures hopefully are lower because of the efficiency I told you about. And then the recovery exposures are way lower because of the optical gain from the homodyne. So I think that was it. So thanks. Sorry to run over.
We have time for only one.
Yeah.
You went through a lot of work to do your incoherent nearest neighbor and figuring out how many pixels you require. In the coherent case, do you have to do that all over again?
I should do that all over again because I've basically gone in the coherent case and used all the parameters that worked well for the incoherent case, and maybe I'm not in the sweet spot anymore.
So there might be another win.
There might be more wins, yeah. The oversampling ratio I don't know about, the size of the polytopic aperture I don't know about. I might be able to do a better job on the coefficients themselves, but yes, that is work yet to be done.
But you have designed a P&Q code. You have designed separate codes for the reserve block locator.
Yes, that part I did. Yes.
Okay, that's Mark again.
Good.